Welcome to our deep dive into HVAC control systems within building management systems, or BMS. In today's world, smart buildings rely on BMS to ensure comfort, efficiency, and safety for all occupants. HVAC, standing for heating, ventilation, and air conditioning, is at the heart of this, consuming the largest share of a building's energy and directly impacting air quality and comfort. In this video, we'll explore how BMS orchestrates HVAC systems, from massive chillers to the smallest fan coil units. Let's set the stage for understanding how technology and engineering come together to create optimal indoor environments. The primary goals of HVAC control within a BMS are clear: maintain ideal indoor temperature, humidity, and air quality, optimize energy consumption, ensure equipment safety and longevity, enable zoning and occupancy-based control, and automate operations based on schedules, sensors, and demand. These objectives drive every decision in system design and operation. By achieving these, buildings not only become more comfortable, but also more sustainable and cost-effective. Let's look at how these objectives translate into real-world strategies and components. A BMS manages a variety of HVAC components, each with a unique role. Chillers produce chilled water for cooling, while air handling units, AHUs, supply and condition air. Fan coil units, FCUs, provide localized air conditioning, and variable air volume, VAV, boxes, modulate airflow to different zones. Pumps circulate water, cooling towers reject heat, boilers provide heating, and dampers and valves regulate airflow and water flow. Together, these components form the backbone of any building's climate control system, working in harmony under the watchful eye of the BMS. Temperature control is fundamental in HVAC. BMS uses modulating valves on chilled or hot water coils, VAV damper positioning, and variable speed fans or pumps to maintain room temperatures at set points. By constantly monitoring sensors and adjusting equipment, the system ensures that every space remains comfortable, regardless of external weather or internal heat loads. This dynamic control not only keeps occupants happy, but also reduces unnecessary energy use, contributing to both comfort and sustainability. Beyond temperature, maintaining proper humidity and pressure is crucial. Humidity is managed using humidifiers or dehumidification cycles, often triggered by room sensors or return air data. Pressure control, on the other hand, ensures that air and water move efficiently through ducts and pipes, typically using variable frequency drives on fans and pumps. These strategies prevent discomfort, mold growth, and equipment strain, ensuring a healthy and efficient indoor environment. Modern BMS systems leverage occupancy sensors to further optimize HVAC operation. When a space is unoccupied, fan coil units can be turned off and airflow reduced, saving energy. In meeting rooms or zones with fluctuating use, the system adjusts conditions in real time. This smart, responsive approach ensures that energy is only used where and when it's needed, aligning comfort with actual building usage and reducing operational costs. Air handling units, or AHUs, are central to large building HVAC systems. BMS monitors and controls key points: supply and return air temperature sensors, COR sensors for demand control ventilation, chilled water valves for cooling, damper actuators for air mixing, fan VFDs for airflow, and filter differential pressure for maintenance alerts. The logic is straightforward. If room temperature rises above set point, open the chilled water valve. If COR exceeds 800 ppm, open the fresh air damper. If supply air temperature is too high, trigger an alarm. This ensures precise, responsive climate control. Variable air volume, VAV, boxes are essential for zoning. Each box has a damper actuator to modulate airflow, a reheat coil valve for added heat, and a room temperature sensor for local control. The BMS adjusts airflow to meet cooling loads and uses reheat only when necessary. Integration with occupancy and lighting schedules further enhances efficiency, ensuring each zone is conditioned based on real-time needs and usage patterns. Chiller plants are the powerhouse of cooling in large buildings. BMS manages start, stop sequences, load staging, and set point optimization. For example, if chilled water return temperature exceeds 9 degrees C, the system starts another chiller. If it drops below 6 degrees C, it stops one. The BMS also operates condenser pumps and cooling towers and rotates operation among multiple chillers to balance wear. This orchestration ensures reliable, efficient cooling even during peak demand. Fan coil units provide localized temperature control, often in individual rooms or small zones. Each FCU uses a room thermostat, a 3-speed or modulating fan, and a 2-way or 3-way valve for chilled water. FCUs can operate independently or be networked to the BMS for centralized monitoring and scheduling. This flexibility allows for precise comfort control in diverse spaces, from hotel rooms to office suites. BMS-driven HVAC systems employ advanced strategies for energy savings. Economizer mode uses outside air when conditions allow, reducing mechanical cooling. Demand-controlled ventilation, DCV, adjusts fresh air based on COR levels. Night setback changes temperature set points during unoccupied hours, and start-stop optimization aligns system operation with predicted occupancy. AI-assisted chiller plant optimization further refines performance, making buildings greener and more cost-effective. Safety is paramount in HVAC control. BMS monitors for high return air temperature, dirty filters, fan failures, valve feedback errors, and freeze protection. When an alarm is triggered, the system alerts operators and can initiate protective actions, such as shutting down equipment or adjusting set points. This proactive approach prevents damage, ensures occupant safety, and reduces downtime, keeping building operations smooth and reliable. Modern BMS front ends provide real-time graphics of AHUs and VIVs, with animated valves, fans, and dampers. Trend graphs display temperature and airflow over time, while alarm logs record events and operator actions. These visual tools help facility managers quickly identify issues, optimize performance, and ensure that every system is running as intended. The integration of data, visualization, and control is what makes BMS so powerful in today's smart buildings. In summary, HVAC control is the core of BMS functionality, requiring seamless coordination between sensors, controllers, and mechanical devices. Through precise logic and continuous feedback, BMS ensures comfort, safety, and energy efficiency across all building zones and equipment. As buildings become smarter, the role of BMS in managing HVAC systems will only grow, shaping the future of sustainable, comfortable, and efficient environments for everyone.